Hey, welcome back. We are working on this assignment right here, isosceles triangles. This corresponds with section 4.6 in your textbook, this section right here. So if I didn't already mention that, this section starts on page 216, and the theorems that we've been talking about are on 216, the bottom of 216, and then 218 here. And in this video, we're actually doing the second part. So in the previous video, we talked about this guy right here, theorem 4.9. We talked about how to write a converse. We talked about the proof of the converse. And again, those are all kind of in your textbook there. So in this video, we're going to take a look at what we call corollaries. Okay, so I kind of wrote this out just because there's a couple proofs here. I wanted to make sure I had them down for you and give you kind of a guide. Now, I don't want you to copy this thing down without thinking about it. Okay, I know that sometimes proofs are hard for people, and some of these questions are a little bit, tricky. So I want to try to help you get the rest of the way there, but I also want you to understand as you do it. Okay, so let's take a look at corollary 4.3. Okay, now a corollary is like a theorem. It's essentially a mini theorem. Okay, when you prove something and you get an extra result, sometimes that extra result is called a corollary. Okay, so corollary 4.3 says a triangle is equilateral if and only if it is equiangular. Okay, now equiangular just means all the angles are the same, so you can see that these are marked congruent. Okay, so there's a couple things we want to talk about. The first idea is, what does if and only if mean? And the other idea is, does this even make sense to us? Okay, well, if you think about it, we just proved two theorems about isosceles triangles. Okay, what we proved is, in an isosceles triangle, the base angles are congruent. Or if two angles of a triangle are congruent, then the angles opposite those sides are congruent, right? We also learned it the other way around. If two angles are congruent, then the sides opposite those angles are going to also be congruent as well. So think of an equilateral triangle as just an isosceles triangle from several different perspectives. So if I'm talking about these two sides, then these two angles must be congruent. But if I'm talking about these two sides, then these two angles must be congruent. But if I'm talking about these two sides, then these two angles must be congruent. So essentially, we're just looking at the equilateral triangle as like an isosceles triangle from every direction. And the same is true the other way. If these two angles are congruent, then these two sides must be congruent. But if these two angles are congruent, then these two sides must be congruent. But if these two angles are congruent, then these two sides must be congruent. Okay, essentially that's just using theorem 4.10, 4.10 I guess I should say, and 4.9 that you already proved. Okay, so that's what that theorem, that's where that theorem comes from. I didn't ask you to do a proof of that because I think that's, kind of obvious when you talk about it. But what I did want you to talk about is this if and only if idea. Okay, so if and only if is the language of what we call a biconditional statement. Okay, so we're going to take a look at biconditional statements for a second. This is on page 81, and that's written down in your assignment as well. So on this page, you learn about what a biconditional statement is. So let's look at an example here. Okay, so notice that we have two statements. Ashley earns $15 an hour, and Ashley works over 40 hours a week. So if P then Q is a conditional that says if Ashley earns $15 an hour, if Ashley earns $15 an hour, then she works over 40 hours a week. Sorry. The converse of that statement is just the opposite direction. If Ashley works over 40 hours a week, then she earns $15 an hour. So when a statement is true, its converse isn't necessarily true. But if they are both true at the same time, you can put them together into what's called a biconditional statement. So here's an example of the biconditional. Now notice the arrow is going in both directions. Ashley earns $15 an hour if and only if she worked over 40 hours a week. So this if and only if is basically an arrow that goes in both directions. Okay, so this guy here, this biconditional statement, is read P if and only if Q. And what we know again is that when we see something like that, then the statement works both directions. P implies Q works, and also Q implies P works. In other words, a statement and its converse work at the same time. Now again, that's not always the case, but if you have a biconditional, then it works in both directions. So you'll notice when we flip back to where we were at in chapter 4, let's look at this corollary again. Okay, a triangle is equilateral if and only if it is equal angular. So this is a statement that works in both directions. So what we could say is, if a triangle is equilateral, then it is equal angular. If a triangle is equal angular, then it is equilateral. It works in both ways, just like working 40 hours a week, $15 an hour. $15 an hour, working over 40 hours a week. Okay, if and only if, again, tells us we have a biconditional statement, which means it works in both directions that we want to write it. In other words, a statement and its converse is true. Okay, so over here, what I have is I have written it down, and I actually drew a little arrow here, if and only if, just so I know that this statement can go in both directions. Okay, so if and only if, what does it mean? It means the statement's a biconditional statement. It means it works, it's true in both directions, or the original statement and the converse are also true at the same time. So that's kind of the idea there. So if I were to turn it into two conditional statements, the first one would be, if a triangle is equilateral, then it is equal angular. The reverse direction was, if a triangle is equal angular, then it is equilateral. Okay, so when we have the if and only if, again, we can write it in two directions, and that's what they look like. Okay, each one of these is a conditional statement. This is the converse of this, and they both happen to be true. And so we can put those together into a single biconditional statement, which is what they do in the book. Okay, so I wanted you to kind of understand what a biconditional statement was and how to interpret one. All right, then we have another corollary. That's 4.4, okay, and it says each angle of an equilateral triangle measures 60 degrees. Now, we didn't formally prove corollary 4.3, but we kind of talked about the reasoning, and so I'm going to allow you to use corollary 4.3 in your proof of corollary 4.4, and that's what I have down here. Okay, so let me get my book out of the way. Okay, now again, I'm going to give you this proof because sometimes it's hard to know where to go. But what I want you to do is I want you to study and make sure you understand this proof. So what I would do is go through this proof with me. Don't write it down word for word right now. Understand the idea, then pause the video and see if you can rewrite it on your own. If you need to unpause the video, you can do that, but the idea here is not to copy this straight down. I want you to understand the reasoning because you may see this again on a test or quiz. Okay? So I started with an equilateral triangle. This corollary wasn't written in if-then form, but if I wanted to force it to be if-then form, it would basically say, if a triangle is equilateral, then the measure of each angle is 60 degrees. So the if part is that I got an equilateral triangle. The then part is that I want to show that all these angles are 60. Okay, so I start with ABC is an equilateral triangle, given. Now we just talked about corollary 4.3. Now remember, we're proving, sorry, this is a typo, I should say corollary. We're proving corollary 4.4, but we can use corollary 4.3. So corollary 4.3 said, hey, if this guy is equilateral, then it's also equal angular. We just talked about that, how that corollary goes in both directions. Okay. All right, well, if it's equal angular, what does that even mean? Equal angular means all the angles have the same measure. So my next statement was measure of angle A equals measure of angle B equals measure of angle C. They're marked congruent in the figure, but basically equal angular means they're all congruent to each other or they all have the same measures or whatever. Okay, so A and B and C are all equal to each other. The other thing we know, though, let me zoom in really quick here so you can see this, is that the sum of the angles for any triangle are 180. Okay, that's called the angle sum theorem. We proved that early last week. So the measure of angle A plus the measure of angle B plus the measure of angle C has to equal 180. So these two ideas are really important here, and we're basically going to combine them into step 5. If the measure of A is the same as the measure of B, which is the same as the measure of C, then I can replace the measure of angle B with angle A whenever I see it. The same thing is true with angle C. I can replace the measure of angle C with the measure of angle A because they're all equal to each other. So what I've done here in step 4 to step 5 is I replaced the measure of angle B with the measure of angle A because those are the same number. And I replaced the measure of angle C with the measure of angle A because those are the same number as well. I don't know what number yet, but I'm trying to show that that number has to be 60. Okay? I just know right now that they're all the same number. So now I have the measure of angle A plus the measure of angle A plus the measure of angle A equals 180. Now that seems a little silly, but we're going to be able to figure out what the measure of angle A is using some algebra. So I'm substituting in that step. I replaced the measure of angle B with the measure of angle A because they're equal to each other. I replaced the measure of angle C with the measure of angle A because they're equal to each other. And that's substitution. Now think of this like a variable. Right? This is just some number. We're assuming maybe 60, 60, 60, but we don't know that for sure yet. But if I have 3 measures of angle A, I can kind of like combine like terms here. So 3 times the measure of angle A is the same thing as adding the measure of angle A to itself 3 times, basically. So 3 times the measure of angle A equals 180. And now what I can do is I can divide both sides by 3. Okay, that's going to get rid of this guy, and it's going to give me 60. So the measure of angle A has to be 60 because 180 divided by 3 is 60. That's going to be the division property of equality. Okay. Now, since A and B and C are all equal to each other, I already said that they were, then I also know the measure of angle B is 60 and the measure of angle C is 60 by substitution. All right, so again, it's kind of the old substitute and divide out what you don't need or subtract out what you don't need. So similar kind of idea we've done before. All right, so that's the proof of that theorem. Now again, if you didn't know how to do that, if you had no idea where to start, now you understand that. So think about that for a second. Read through it if you need to, but don't copy it word for word. I want you to pause the video and try to write it down without looking so that you can understand that logic. Right? It's not about just copying it so you can get the assignment done. It's about understanding what's happening here, understanding this chain of reasoning, and being able to reproduce it in the future. All right. We got one more proof to take a look at, and that is the proof of a theorem from chapter 5. So, looking for my proof that I wrote out. There it is. All right, here's this one. Now again, don't copy this down. I mean, you can use this to help you finish your homework, but don't just copy it down. Okay, I want you to understand it. So don't write this down yet. Watch the video, follow my chain of reasoning, and then try to write it on your own. All right, before we get too deep in this, we're going to look up the actual theorem in the textbook so you can see what it looks like. And then we'll kind of explain where we're going from there. Okay. So theorem 5.1 says any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. All right, well that's a little wordy, so we're going to have to break that down. Okay, first of all, what do we have? We have a segment, CD. See that guy? Okay. Now for that segment, there is a perpendicular bisector. That's this guy, AB. Okay? Perpendicular means that they make a right angle. Actually, 2 right angles here. Bisect means it cuts it into 2 congruent segments. Okay, so you'll see that we have a right angle, we have 2 congruent segments. So AB is the perpendicular bisector of CD. That's the if part. If a segment has a perpendicular bisector, then the point on that perpendicular bisector, in this case A, actually could be B as well, but we're just going to talk about A, has to be equidistant from the endpoints from C and D. Okay, equidistant means they're the same distance away. So what we're trying to prove here is that the distance from A to C is the same as the distance from A to D. Well, if you think about it, you got 2 triangles right there, right? So the proof of this, even though it's kind of in like the next chapter, is actually really, really similar to the proofs that we're using today, which is why I think it makes sense to add this together. So to set up your proof, you're going to start with a picture. Okay. Now I set up my picture kind of similar to the one in the book, only I don't have the bottom part. Okay, you don't really need the bottom part. But here's the idea. I start with a segment, CD. Okay? Then I want to draw what's called a perpendicular bisector. Now this is actually a construction that we did not too long ago. We did it with compass and straight edge. But this line, AB, I drew as my perpendicular bisector, which means I got a right angle here, and I got a right angle here, and I got congruent segments. Bisect means cut into two congruent segments, or two congruent angles if you're talking about an angle bisector, but this is a segment bisector. And perpendicular means it forms a right angle. Okay? So our goal is to show that these two endpoints of the segment, or excuse me, I should say it the other way around. We want to show that A, the point, notice this point is on the perpendicular bisector, is the same distance from these two endpoints, C and D. Okay, but when you connect those dots, you get a triangle, right? So what we're trying to show, now we're not going to assume this, but what we're trying to show is that these two guys are congruent. Okay, if we can show those two segments are congruent, we're basically showing that the distance of A from C is the same as the distance from A to D. Okay, so given AB is the perpendicular bisector of CD, right? That's the kind of the if part of the theorem. Now it doesn't say, it's not written in if-then form, but basically it would be if a point is on a perpendicular bisector of a given segment, then it is equidistant from the endpoint of that segment. Okay, so we're going to assume we have a point, like point A, on the perpendicular bisector of this segment CD. What we're going to try to prove is that AC is congruent to AD. In other words, the distance from A to C is the same as the distance from A to D. Okay, so we start with the given. Now this symbol right here, upside down T, it means perpendicular. So AB is perpendicular bisector of CD, given. Okay, now perpendicular gives us right angles. So my next statement was that CEA and DEA are both right angles. Definition of perpendicular. Now from there, I actually did this a little bit later. You could do it right after this step if you want. It doesn't really matter where you do it. But later on, I say that, look, if these two guys are right angles, then they're congruent to each other because all right angles are congruent to each other. So we have a pair of congruent angles from like line 2 and 5. These actually kind of go together, but it doesn't really matter where you write them. Okay, the other thing I know in step 3 is that CE is congruent to DE, definition of bisect, right? I cut CD into two congruent pieces, okay? And then the other thing is that AE is a segment that's on both triangles. I actually added this point E. It's the midpoint here of CD just to help me label stuff. So you don't actually see that point labeled in the book, but you can label any point you want. Okay, so AE is congruent to itself, reflexive property. So notice I got the angle, right? And I got a side and a side. And in reference to my picture, I basically have side, angle, side. Now remember, we're trying to show these are congruent, so although it looks like I have another side there, I didn't have that as part of my assumption. That's what I'm trying to prove. Okay, so now this triangle, ACE, is congruent to ADE by SAS, because I have this side congruent to this side, I have this side congruent to itself, and the included angle, they're both right angles, and so they're congruent to each other. Okay, as soon as I get the triangle congruent to the other triangle, I can use CPCTC. We can prove these triangles are congruent with a minimum information of side, angle, side, but as soon as we prove that they're congruent, all the other sides fall into place. So I know that these two guys have to be congruent to each other, and I also know that these two angles have to be congruent to each other, and I also know that these two angles have to be congruent to each other. Okay, now that's not necessarily what we're trying to prove. We're trying to prove this segment is congruent to this segment, which we can do by, again, CPCTC. Okay, now what you're going to do here, that was all the in-class stuff. So if you worked hard today and you were focused and you weren't, talking too much, you finished that in class. If you weren't here, then now you have it, okay? After all that stuff, the next step is to go into your book and to do just a few problems, I think 7 from your textbook. So I'm not going to do all of them all the way out, but I'm going to help you set some of them up. Now this will use the two main theorems that we proved today. Basically theorem, I think it was 4.9 and 4.10 about isosceles. Now, one warning that I'm going to give you here is that these triangles are not drawn to scale. So you'll notice that they're using these figures for multiple problems, and so they don't want to draw it in any specific way, because if they do, it may not look right for the other triangle. So it's kind of generic here, and you're going to be like, those don't look congruent, but that's okay. Just go with what it tells you. So in this figure, JM is congruent to PM. So these guys are congruent, which makes this an isosceles triangle. Okay, we also know that ML is congruent to PL. So we have two isosceles triangles. One's kind of on its base and one's kind of on its side. So we have to apply the basically theorem 4.9 it was. So if this is an isosceles triangle, then the angles opposite these congruent sides are congruent to each other. Okay, and in this triangle, these angles opposite of the congruent sides are congruent to each other. So these two bottom angles here are congruent, and then these two angles are congruent. We also know that these two angles form a linear pair, and that may come in handy in a second. Okay, so PLJ, that's this guy, is equal to 34. Okay, and we want to find the measure of JPM. That's this guy right here. Well, if this is 34 degrees, then if we do 180 minus 34, that will give us the other angles, like the rest of the angles together. Now there's 3 of them, but we also know that they're the same. So what I'm going to do is I'm going to do 180 minus 34. So now what I know is that the sum of these two angles has to be 146. But remember, they're exactly the same angle. So I'm going to take 146 and divide it by 2, and that's going to give me 73. So each of these guys are 73 degrees. Okay? All right, sorry, it's getting a little messy here. Let me go back and erase some of this. Okay, so we got this is equal to 73 degrees. Now, these two guys form a linear pair, right? So if these are a linear pair, then this one has to add to 180 with this one, which means that this guy has to be, let's see, 107. I'm starting to second guess myself. These angles look a little bit too big. Let me double check what I had before. So I had 180 minus 34, that was PLJ, that's this guy. Okay, 146 divided by 2, 73. Okay, just double checking because this is starting to freak me out a little bit. Okay, so let's do 180 minus 73. Okay, that makes this guy 107. But then that would mean that this guy is 107? That's strange. JPM. I'm going to have to think about this one. So come back in the next video and we'll talk about this one because something happened here. I must have done something wrong or there's a typo or something. So I'm going to have to consider this one and then I'll come back and explain what's going on.